Good day everyone, I am Manuel Maglunob of BSECE3A and I will present to you my performance task on module number 7. And in this activity, I picked 3 terms that corresponds to the initials of my name, which is M, P, and M. So the first M stands for mode field diameter or MFD, P stands for planar waveguide, and M for misalignment loss. So let's get started. So mode field diameter or MFD. So MFD is the diameter of the one mode of light propagating in a single mode fiber slightly larger than the core diameter. And in fiber optics, the mode field diameter is a measure of the width of an irradiance distribution such as optical power per unit area across the end face of a single mode fiber. So what is an MFD? So mode field diameter is a measure of light intensity in a single mode fiber cross-section. Traditionally, MFD is the width of the curve where the intensity falls below 1 over E squared or e raised to negative 2 of its peak. While still a good way to visualize the MFD, the definition has improved. International standards define MFD via the Peterman II definition, which involves integration of angles obtained from the far field intensity distribution, and MFD as the effective area of the fiber is larger than the core, with light also propagating through a portion of the cladding. So here, there is an illustration of the mode field diameter. So mode field diameter is slightly larger than the core, if you can see on the image. On the center, we can see the gray colored part, that is the core, and the region bounded by the broken lines is the MFD. So MFD is basically a core and a small part of the cladding. So here is an additional illustration of the MFD. So here we can see that MFD is a core and a part of a cladding, and there is a portion of light travels through the cladding. And here is a 3D graph of an MFD. And here, additional 3D graph of the MFD. So, application of the mode field diameter. So, it is important because, as a measure of the size of the optical field itself, it enables you to design launch optics to match the mode of the source to that of the fiber and to maximize launching efficiency. So let's go to the planar waveguide. So planar waveguide is a flat waveguide formed on the surface of a flat material. The zone of high refractive index is rectangular in cross-section and guides light in the same way as the core of an optical fiber. So planar waveguides are waveguides with a planar geometry which guide light only in one dimension. They are often fabricated in the form of a thin, transparent film with increased refractive index on some substrate, or possibly embedded between 2 substrate layers. So here is a planar waveguide. So it is a planar dielectric slab waveguide. So a slab of dielectric of refractive index N1 is sandwiched between 2 semi-infinite regions, both of refractive index N2, and N2 is less than the N1. So the core is the region of higher refractive index represented by N1, and the cladding is the region of lower refractive index represented by N2, sandwiching the core. So a light ray can readily propagate along such a waveguide in a zigzag fashion, provided it can undergo total internal reflections or TIR at the dielectric boundaries. So, waveguide mode numbers. So for better understanding, we have to compare the planar waveguide on the other mode of waveguide. So we compared it to the cylindrical waveguide. So planar waveguide is bounded only in one dimensions, and it has reflections occur only in the y direction, only one mode number M, while in cylindrical waveguide, it is bounded in 2 dimensions, reflections occur from all the surfaces to mode numbers L and M. So here is their image or illustrations. So applications of planar waveguides. So planar waveguides can be used to interconnect the various parts of a microwave amplifiers. So in the image, there is a microwave amplifier. So also, planar transmission lines can be used to feed microwave energy from a microwave generator to an antenna as shown. And another, planar waveguides also can be used to design filters and phase shifters. So the first image is the filter and the second image is the phase shifter. And next is the misalignment loss. So misalignment loss in waveguide design and construction, angular misalignment loss is power loss caused by the deviation for optimum angular alignment of the axis of source to waveguide, waveguide to waveguide, or waveguide to detector. The waveguide may be dielectric or metallic. The loss of power resulting from angular misalignment, lateral displacement, and end separation. So those three are the three types of misalignment loss. So first is the longitudinal misalignment or the end separation, where the two fibers are not connected. Second is the lateral misalignment, where they are not aligned well. And lastly is the angular misalignment, where the two fibers don't form a 180 degrees, so they are not connected properly. So these losses depends upon the fiber type, core diameter, and the distribution of the optical power. So losses due to geometric variations. So misalignment may occur in three dimensions: the separation between the fibers, so that is the longitudinal misalignment, or the end separation, and next is the offset perpendicular to the fiber core axis, which is the lateral misalignment, and the angle between the core axis, or the angular misalignment. So here are other forms of misalignment. So there is a lateral offset, an angular misalignment which is mentioned earlier, the NA mismatch, the core diameter mismatch which is similar to the end separation, the concentricity, the ellipticity or ovality, and the cladding diameter mismatch. So here is their graphs. So losses due to longitudinal and lateral misalignments. So our y-axis represent the insertion loss and our x-axis represent the displacement. So if you can see, in the lateral misalignments, after reaching about the value of 15, the insertion loss drastically increases, while in the longitudinal misalignment, as the displacement increases, the insertion loss gradually increases or slightly increases. So we can say that lateral has a higher insertion loss, and losses due to the angular misalignment. So the losses due to angular misalignment depends on the type of gap. And that's all for this activity. Thank you and God bless.